Okay. Section 3 then, or 1.3. Look at that. Trying to alleviate the weird sort of, oh great, that just made my shadow worse. Let's see if we can move it over here. I don't have a big shadow. Just fighting shadows. Okay, anyways, 1.3, more on functions and their graphs. So we can use graphs to model all kinds of things in reality, and we want to zoom in particular some characteristics of these graphs that will be important for us for our work. The first thing we take a look at the increase and decrease of these graphs. In particular, where is the graph increasing, where is the graph decreasing? Okay, so we have some very technical definitions for all of this, and we start with increasing. Increasing. Okay. So in particular, if x1 is less than x2, then that will tell us that f of x1 is less than f of x2. Okay. So in particular, you have these 2 points, x1 and x2, and then you have f of x1 and f of x2. So you can see it easier on the graph that the thing is increasing. Okay, so f of x1 is less than f of x2. So this is an increasing graph. It is what you think it is, right? It's going up. Okay. It's just we need this nice definition to make things very rigorous. Okay. And we have decreasing, so same sort of definition. If x1 is less than x2, you can almost sort of guess what's coming. Then the first value will be less, or rather greater than the second value, f of x2. So you can imagine the graph here in this case will look something like this. Okay. So f of x1, the height of the first one will be greater than the height of the second one. And of course that's not it. You can also have functions that stay the same throughout. And we're going to call those constant functions. Right? So in those cases, f of x1 will actually just equal f of x2 for all x1, x2 in some interval. Okay, so the first set of problems in the book will have you identify the open intervals on which the function is increasing, decreasing, and constant. Okay, so let's take a look at some of those. It's problem 2 in the book. We have a parabola. I'll try to give you the exact points here. So -3, 0, 1, 2, 3, 0. And then 0, 3, and then -1, 4. 1, 4. So something like this. Okay, so where is it increasing? Well, it's going up, literally, from -infinity into to that point. Right, so we can sort of do a little table here. Increase, we're going to need the interval of decrease, and then where is it constant? So it's increasing from -infinity to whatever this point is here. I think it's at -1. And you could tell in the book, so it's not like I'm using algebra to figure that out or something. It's just literally I'm looking at the graph. Okay, so where is it decreasing? Well, it's decreasing from that point on. So it's from -1 to infinity, it'll be decreasing. And then it's really not constant anywhere. Okay, so in that case, you'll just write no. Okay. Let's look at another one. Number 8 is a bit odd. Not the typical kind of graph we're used to dealing with. On the left here, it's on the negative x-axis. Okay, it's literally sitting right here. And then it jumps up from that point on, and it goes through the point 2, 4. So it goes through this point here. So again, we have the interval. We need the interval of increase, the interval of decrease, and then is it constant anywhere? So it's increasing from 0 on, right? So we'll put in 0 to infinity, and it's not decreasing anywhere. So we'll just write no. Constant then from negative infinity to 0. So it just stays the same in that interval. That's it. Okay, so another thing we'll be worried about is the max and min. You can see in this picture there's a maximum at the vertex. You may remember that from basic algebra. They wanted you to find the vertex to solve some application problems involving maxes and mins. Okay, so this guy has a maximum right here. So in general, we'll be looking for relative maxes and relative mins. Because some functions, for example, polynomials, maybe they'll have a couple dips and valleys. Okay. And if you sort of used your viewing window on your calculator and maybe looked right here, it'll have a relative min here and then a relative max here, right? I mean, it's not the absolute min and absolute max, because the absolute min would be this guy over here, and then this guy wouldn't be an absolute max because there's a max here. But in this little window, you know, relative to this little window, this is a min and this is a max, and that's what we mean by that. And the book will give us a big, nice, long definition for that. But in a nutshell, that's really what they're talking about. Okay. Okay, so maybe we can write, hey, look at this. This is a relative, you know, relative to the window. This is a min. And then this point up here, relative to the window, this is a max. If you keep taking math, they'll make that very rigorous, and we'll find all kinds of nice methods for determining those points. I think for now we just want to be able to identify them. Okay, the next section then is on symmetry. Okay, so you probably noticed in the case of parabolas, they have, I mean literally, they have an axis of symmetry on them. Okay, we want to take that up a notch and ask ourselves, you know, for a randomly generated equation, is there any sort of symmetry that we can hang our hats on? Okay, and there'll be 3 types in the beginning that we'll concern ourselves with. There's the x-axis symmetry, which we'll later call even symmetry. Okay, so for x-axis symmetry, you'll have a scenario like this. If the point xy is on the graph, then automatically the point negative xy is on the graph. Then we also have y-axis symmetry. Okay. Whoops, this is y-axis symmetry, sorry. We also then want x-axis symmetry. So for x-axis symmetry, if the point xy is on the graph, then the point x negative y is on the graph. Okay. And the final kind of symmetry is the origin symmetry, which we'll later call odd symmetry. So we have graphs like these have that kind of symmetry. And in those cases, if the point xy is on the graph, the point negative x negative y is also on the graph. Okay, and we have algebraic tests for these. So you may not be able to graph them accurately, or even if you did have a calculator, find the appropriate viewing window. And even if you had that, you couldn't legitimately say, okay, this is 100%. I can tell it's symmetric. I mean, you could eyeball it, but in general, eyeballing is not going to be good enough. Okay, so you need to have these other methods for determining symmetry, and the methods will be for x-axis symmetry. You need to sort of plug in negative y for y. For y-axis symmetry, you need to let x equal negative x, and let's just show you, right? So we'll look at checkpoint 2. Check y equals x squared minus 1 for symmetry. Right? And we kind of, you may know what this graph is. It's just a parabola right here. So it's going to have y-axis symmetry, and then not x, not origin symmetry. Okay? But let's go through the motions, so to speak. So first, for x-axis symmetry, what you're going to do is replace y with negative y and see if you end up with the same equation. Okay? So I'm replacing y with negative y, and then trying to turn it into this guy here somehow. Is it possible? And it's not. Okay, so you could try multiplying both sides by negative 1, you get negative x squared plus 1. This guy and this guy are not going to be the same thing. Okay, they may have points in common, but they're not going to be the same picture. Okay, so in that case, you'll say no, which is what we suspected. From looking at the actual graph, it's not symmetric about the x-axis. Okay. And then y-axis, yeah, it is. Let's make sure. So for y-axis symmetry, you need to replace x with negative x and see if it leaves it unchanged. Okay, so I replace x with negative x. Okay, so I'm using good notation. I put the negative x in parentheses, squared. And then I'm going to simplify. Negative x squared is positive x squared. Okay. And then that is exactly the same as the original equation. So yes, there is y-axis symmetry. Yes. And then finally, origin symmetry. So for this, we do the double trouble, sort of, so to speak. We're replacing x with negative x and y with negative y. Okay. So I have negative y equals negative x squared minus 1. And I'm trying to see if that's the same as this. So I'm going to square this up. I'm sort of simplifying. And already I'm kind of in trouble, right? I have the same scenario that I saw in the x-axis case. If you try to multiply both sides by negative 1, it's not going to give you the original equation, so therefore, no, it doesn't have that kind of symmetry. Okay. Let's look at let's look at 38. So I have f of x equaling x cubed minus x. Again, I need to go through all these symmetry tests and see what's going on. So x-axis, I need to replace y with negative y. So I'll have negative y equals x cubed minus x. And it's immediately obvious, at least to me, that's not going to work. You can multiply both sides by negative 1. And this guy is not the same as this guy. Okay? So no. Let's try y-axis. So for y-axis symmetry, you need to replace x with negative x. So I'll do that using my parentheses and good notation. negative x cubed is just negative x cubed. Okay, a negative to an odd power is still negative. And then we have negative times a negative is positive. Okay. And then again, this is not the same as that guy. So new. Then finally, we want to look at origin symmetry. And in those cases, we replace both y and x with negative y, negative x. Okay. So I'm going to simplify here. And then I'm going to multiply both sides by negative 1. And, oh, look, well, yeah, that is exactly the same as what we started with. So therefore, yes, this guy does have the origin symmetry. Okay. Okay, so with regards to functions, then, there's an issue with these types of symmetry. In particular, a function is not going to have the issue of x-axis symmetry. Because if it had a symmetry about the x-axis, it wouldn't necessarily be a function at that point. So the kinds of symmetry that we in general are going to be concerned with are the y-axis and the origin symmetry. And the y-axis symmetry will be even, we'll call it even. And then for origin symmetry, we'll call that odd. Okay? And we'll change the test. Ultimately, it's the same kind of test that we'll be doing here, but it'll look a bit different. Okay, so section 4, even versus odd functions. Okay. And we'll start with even. So for the y-axis symmetry, we replace x with negative x. So the way it's going to work is in the function, we're going to put a negative x in there. And if f of negative x is equal to f of x, so if it ends up being equal to the same thing it originally was, then it's an even function. Okay, so let's look at 41. And we want to figure out if this guy's even or not. It turns out it is. Okay, so it's polynomial f of x equals x squared minus x to the fourth. And I'm going to figure out what f of negative x is. Right? So I'm going through and I'm putting negative x in for x. Okay. And when you raise a negative to an even power, it becomes positive. So this will be positive x squared minus positive x to the fourth. Okay. And this is f of x. Okay. And that's what we were trying to show if we were trying to show it's even. Right? F of negative x is equal to f of x. Okay, so this guy is definitely even. Okay. Then secondly, the odd version. So if we have f of negative x, back here we would replace negative y and negative x. Replace y with negative y and x with negative x. Here, to show it's odd, we want to show that f of negative x is equal to negative f of x. It's the same kind of deal as showing it was odd up here, or showing it had origin symmetry up here. So in particular, let's look at 47. And we have f of x equaling x square root of 1 minus x squared. Okay? So certainly, I'm not going to be able to imagine what this thing looks like and say, oh, it's odd. No, you need some sort of trick, algebraic trick to determine if it's odd, and we've supplied that. So I'm looking at f of negative x. Okay? So I'm replacing x with negative x everywhere I see it in the function. Using good notation. And I'm simplifying, so I have just plain old negative x, and the square root of 1 minus negative x squared is x squared. Okay. And this is negative f of x. If you don't see it, you can rewrite it as negative, and then we have x times the square root of 1 minus x squared. but that's just a negative in front of f of x. That literally is negative f of x. Okay? And that's what you're trying to show when you're looking for oddness. Okay, this is definitely odd, because f of negative x is equal to negative f of x. Okay, a couple more issues. We want to deal with piecewise functions. Okay, so a lot of the functions we've been looking at are kind of, not going to get us very far in the modeling game. So we'll need piecewise functions to deal with real-world situations. And piecewise functions are just what you think they are. There's pieces of functions, and they sort of smush them all together. First, we'll just take a look at evaluating. Okay. Particular 54. We have f of x equals 6x minus 1, and we have a 7x plus 3. And particular here, if x is less than 0, and here if x is greater than or equal to 0. We want to evaluate that thing. Okay. So part A, f of negative 3. Okay. So the deal is you're kind of picking the function based off of the x value. So in this case, negative 3 is less than 0. So you have to use this first part of the piecewise function. Okay. So I'm plugging negative 3 into 6x minus 1. Okay, then I only want f of 0, so 0 is not less than 0, but 0 is greater than or equal to 0. So we're actually in this part of the function, so I got to plug 0 into 7x plus 3. Okay. Finally, 4. 4 is greater than or equal to 0, so it's in the second piece of the function. So it would be 7 times 4 plus 3 is 28 plus 3 is 31. Okay. So once you get the hang of that, that's not so bad. The harder part is actually graphing these things. It's not so bad. You just graph each piece kind of separately. Okay, so graphing, and we want to look at number 68. So we'll have f of x equaling negative 1/2 x squared if x is less than 1. And then 2x plus 1 if x is greater than or equal to 1. Okay. So in the case x is less than 1, we're actually working with this function. Okay. And we'll use values less than 1 all the way up to 1 and see what's going on. So I'm just going to pick a couple of values for this. Well, let's pick negative 4, 0, all the way up to this frontier, this point 1, which is right in between the two pieces. Okay. So negative 4 into here, we'll have negative 1/2 times negative 4 squared. Negative 4 squared is 16. 16 times negative 1/2 is negative 8. Okay. Plugging 0 in, we'll have negative 1/2 times 0. That'll be just 0. Then negative 1/2 times 1 squared. And that'll be negative 1/2. Okay. So that's our first piece. Have some points there. For our second piece then, might as well get that started. X greater than or equal to 1, we just have the equation of a line. Again, I want to include this point that's in between the two pieces, right? So I want to include 1, and then maybe a couple extra points, 2, and then 3. Okay. So plugging 1 in here, 2 times 1 plus 1 is 3. Plugging 2, 4 plus 1 is 5. And then plugging 3, 3 times 2 is 6 plus 1 is 7. Okay. And then I'm going to graph these guys. So there's two parts. I'm going to need go down to 8 here. 1, 2, 3, 4, 5, 6, 7, 8. I need to go up to 8 probably. 1, 2, 3, 4, 5, 6, 7, 8. And then in the x direction, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'll do this guy first. Negative 4, negative 8, negative 1, 2, 3, 4, negative 8. And then 0, 0. And then 1, negative 1/2. At this point, because it's less than, it doesn't have that line underneath, now I'll put an open dot there. Okay? So it doesn't really exist on this graph, but it's kind of like a hey, this is where we stop. Okay, so 1, negative 1/2, and then there's an open dot right there. Okay, so the graph will be smooth right to there. Okay, now I need to graph this guy, and because it has the line underneath, I use a closed dot for the first point. So at 1, 3, I'm putting a closed dot there, just like that. And then 2, 5, 1, 2, 3, 5, and then 3, 7, 3, 6, 7, and we have a straight line for that part of it. Okay? So you just take it easy and do each piece, do one piece at a time. You've got to do tables. You do a table for each, and then you plot each part at the sort of intersection of these guys. Supposing it's there's no line underneath, you're going to use an open dot, but when there is a line underneath, it's included, so you use the closed dot. Okay. The next part is sort of talking about slope. It doesn't seem like it, but I think it's kind of obvious if you think about it. They call it the difference quotient. So just as a warm-up, we know about the slope of a straight line. We'll talk more about that and give you a review of that later on. So the slope of this line is negative. It's falling to this direction. It has a constant slope. At any point on it, it has kind of the constant sort of tilt to it. Okay, so that's great. We want to talk about slopes for more complicated functions. So in certain places, it's going to have different kinds of slopes. Right here, it'll have like a positive slope. Over here, it'll have a negative slope. Okay? So over here, the formula for slope would be, if you remember, m equals y2 minus y1 all over x2 minus x1. Okay? And we also write that as change in y over change in x. You may have seen that notation as well. Okay? We want a slope formula for this stuff here. And it's going to look a bit odd. Okay? And I'll cheat a little. I'm going to write slope. But it looks like this, okay? So it's f of x plus a change in x minus f of x all over the change in x, okay? These are your y values, and then the change in x is just the x2 minus x1 thing, okay? Our book isn't going to use this change in x notation. What they're going to do is the h notation. This. Okay, but what this really is just kind of a slope formula, but it's more relaxed, okay? So the slope formula for the straight line, it's always the same. We want something that's going to handle any sort of curvy function, and that's why we came up with this sort of slope formula. Okay? So this guy is the difference quotient, and we want to play around with that in the homework. We want to play around with this new formula. We're not going to use it really in this class, but if you kept taking math, you would. So, for the people who are going to keep taking it, we need to get really good at it. Okay. Okay, so f of x is 6x plus 1. We know the slope, right? So if we remember our slope-intercept form, it's y equals mx plus b. So the slope is 6. And I'm hoping that I'll get the same answer if I use this formula. I use the difference quotient. I probably will, right? So let's take a look. F of x plus h minus f of x all over h. Okay? And what I need to do is evaluate these functions, right? So for the f of x plus h, I'm putting x plus h in for x. So this will be 6 times x plus h plus 1. Okay, that's this. And then minus f of x. So f of x is just 6x plus 1, so I just put that in there. And then that'll be all over h. Okay. Now you want to distribute and combine like terms and simplify. Okay, so this is equal to 6x plus 6h plus 1. Distribute the negative. Minus 6x minus 1 all over h. Okay. 6x minus 6x is 0. 1 minus 1 is 0. And you're left with 6h all over h. Okay. The h's divide out. Oh my gosh, what did we get? We got the slope. Okay, so hopefully I've convinced you a little bit that this difference quotient is nothing new. It's just a more flexible version of the slope formula that you learned in basic algebra. Okay. So we want to end with a harder version of that. It's more algebraically intense. Not that bad. Believe it or not, if you keep taking math, these things can get incredibly complicated, which is, it's hard because we teach people who are actually going into math. We teach people who aren't going into math. And so we need to find a nice balance. We don't want to mislead the people at going into math. It could get very, very complicated, much more complicated than anything we'll see here. Okay, so hopefully you know that if you're choosing to go into something math related, it can get very complicated. And hopefully you appreciate that. If you're not going into math, this isn't the hardest that it can be. Okay? This is kind of a simple problem, even though it may not look very simple as we go through. All right, so enough said. That's my lecture on that. I'm replacing x with x plus h. So I have negative x plus h squared minus 3 times x plus h plus 1. And then minus f of x, minus negative x squared. You see those parentheses are super important here for us. All over h. I need to go through, I need to FOIL this guy, right? So it'll be negative, and I'm going to keep those parentheses to remind myself I have to distribute a negative eventually. So this will be x squared plus 2xh's plus h squared. Then I'm going to distribute this negative 3 minus 3x minus 3h plus 1. And I'm going to distribute this negative. So plus x squared plus 3x minus 1 over h. Then I need to distribute this negative and combine like terms. So negative, just take one thing at a time. Don't try to do 20 different things in your head. You'll just make mistakes. I mean, some people can, I admit it, but in general, it's better safe than sorry, in my opinion. Okay, so x squares are gone. Let's see. The 3 x's are gone. The 1's are gone. And we're left with negative 2xh minus h squared minus 3h all over h. Okay. We want to get rid of this common factor of h. So you look through here, each one of these guys has an h, and we want to get rid of the fraction. So we could factor out the h from every one of those. So h times negative 2x minus h minus 3 all over h. And then these h's will cancel, leaving us with our simplified form, negative 2x minus h minus 3 And that would be the answer the book is after. And that'll be it. Okay, bye.